Welcome, fellow engineers and tech enthusiasts. Today, we're diving into a topic that's rapidly transforming the landscape of software development: real-time DevOps feedback loops, powered by generative AI. If you've ever felt the pain of chasing down elusive build failures, sifting through mountains of logs, or waiting endlessly for critical insights, then this video is for you. We're going to explore how AI can become your team's most invaluable assistant, providing actionable, instant feedback on your Java builds and tests, right when you need it. Traditionally, DevOps feedback loops can be slow and reactive. A build fails, and developers might spend hours, or even days, manually sifting through logs, trying to pinpoint the root cause. This not only frustrates engineers but also introduces significant delays, slowing down release cycles and impacting overall productivity. Imagine a scenario where a critical bug is introduced, causing integration tests to fail. Without immediate, clear feedback, the developer responsible might only discover this much later, after context switching multiple times, making the fix much harder and costlier. This manual debugging process is inefficient and prone to human error, creating a bottleneck in what should be a smooth, continuous delivery pipeline. But what if you could have an intelligent assistant analyzing your build telemetry in real time? What if this assistant could instantly identify the likely cause of a failure, suggest specific fixes, and even point to the exact lines of code or related commits? That's where generative AI steps in. By leveraging the power of large language models, we can transform raw, often overwhelming, build and test data into concise, actionable insights. This isn't just about identifying a failure, it's about understanding why it failed and how to fix it, all delivered automatically, enabling developers to shift left on their debugging process and resolve issues much faster. So, what exactly do we mean by real-time DevOps feedback? It's the ability to receive immediate, pertinent information about the health and quality of your software as it moves through the development pipeline, specifically during the build and test phases. Instead of waiting for daily stand-ups or sifting through consolidated reports, developers get instant notifications and insights. This shift-left approach empowers teams to catch and fix issues early, reducing the cost of defects and accelerating delivery. For instance, if a unit test fails, the feedback isn't just "test failed," it's "test my application test simulated critical function failure failed due to a null pointer exception, likely in the user service component." Consider checking object initialization. This level of detail, delivered promptly, is a game changer. Let's break down the architecture of a system that delivers this kind of intelligent feedback. At its core, we have three main components. First, our Java application, which represents a typical microservice or module under development. Second, a feedback service, a central intelligence hub built with Spring Boot, responsible for receiving telemetry. And finally, the generative AI model, which, for this demo, is simulated but in a real-world scenario would be a powerful LLM like GPT or Gemini. The flow is simple. The Java application builds and runs tests, its telemetry is captured and sent to the feedback service, which then calls the AI to analyze the data. The AI's insights are then displayed on a web dashboard and can be pushed to communication platforms like Slack or Teams. Our demonstration starts with a standard Java Maven project, Java app, complete with JUnit tests. This project simulates a real-world application, where code changes are constantly being pushed and built. Within this Java app directory, you'll find pom.xml, which handles dependencies like JUnit, myapplication.java, a simple class with some business logic, and myapplicationtest.java, which contains our unit tests. Importantly, myapplicationtest.java includes mechanisms to simulate both passing and failing scenarios, allowing us to control the build outcome for demonstration purposes. This setup allows us to generate realistic build telemetry, including success/failure status, test counts, and simulated error messages. Now, how do we get this build information into our feedback system? That's where the run_build.sh script comes in. This shell script, located within our Java app project, acts as our simulated CI/CD pipeline agent. After mvn clean install runs the tests, run_build.sh parses the outcome. It captures the build status, the number of tests that passed or failed, and crucially, it extracts or simulates specific error messages. These pieces of information are then packaged into a clean JSON payload. Finally, using curl, this JSON telemetry is sent over HTTP to a dedicated API endpoint on our feedback service, effectively broadcasting the build's health to our central intelligence hub. The feedback service is the heart of our intelligent feedback system. Built as a Spring Boot application, it serves multiple critical functions. Its primary role is to act as the ingestion point for build telemetry. When it receives the JSON payload from run_build.sh, it processes this data. Internally, the telemetry service.java orchestrates the analysis by passing the raw build report to the AI service. It also stores a history of these reports, combined with their AI analyses, for display on the dashboard. The feedback service application.java is the main entry point, while buildreport.java, AIanalysis.java, and fullbuilddetails.java are plain Java objects, POJOs, defining the data structures for telemetry, AI insights, and their combined view. The true intelligence of our system resides within the AI service.java. For this demo, we've implemented a simulated generative AI model. Instead of making actual API calls to a large language model like OpenAI's GPT or Google's Gemini, our AI service uses rule-based logic to mimic AI behavior. It inspects the incoming error messages for common patterns, such as null pointer exception, assertion error, or arithmetic exception, cannot divide by 0. Based on these patterns, it generates a concise summary of the issue and provides specific, actionable suggested fixes. This simulation allows us to demonstrate the power of AI-driven insights without the complexities and costs of a live LLM integration, while clearly showing how a real AI would behave. The final, crucial step in our feedback loop is presenting these AI-powered insights to the developers. This is handled by the feedback controller.java and visualized through dashboard.html. The feedback controller exposes a web endpoint at /dashboard which renders an interactive web page using Timeleaf. This dashboard visually displays each build report, color-coded by status, green for success, red for failure, along with the raw telemetry. Most importantly, it prominently features the AI-generated analysis summary and a list of suggested fixes. Concurrently, the telemetry service logs these AI insights directly to the console, simulating real-time, bot notifications that could be pushed to a Slack channel or Microsoft Teams, ensuring developers get immediate, highly relevant feedback. Let's see this in action. The run_demo.sh script is our orchestrator. When executed, it first builds the feedback service. Then, it starts the feedback service in the background, waiting for it to be fully operational. Once the service is up, it triggers the Java app/run_build.sh script twice, first, with a parameter to explicitly simulate a build failure, capturing errors like null pointer exceptions and assertion errors. After a brief pause, it runs run_build.sh again, this time with a parameter to simulate a successful build. This sequence generates both failure and success telemetry, sending it to our feedback service for AI analysis. The script then prompts you to open your browser to http://localhost 8080/dashboard to see the results and observe the bot notifications in the console. Now, let's look at a concrete failure scenario. When the run_demo.sh triggers the simulated failure, the Java app sends telemetry indicating a build failure with specific error messages, like a simulated null pointer exception, user service data